So the new chapter, as I told you, is RBD or rigid body dynamics. Okay. Now here you see. Again, every time I start something and I keep telling, I'll tell you, you have to see that what are the concepts involved, and this subject called physics is built of concepts. Correct? So so now rigid body dynamics. So first of all, you see, body means, well, collection of particles. So that's how we look at it. There are many particles that make up a body, or extended body. We usually call the word extended body. And dynamics here means it's concerned about motion.
Why?
That is, we are dealing with the motion. And this concept of rigid,
Yes.
we have already visited
Yes.
this concept rigid
Yes.
when we studied materials.
Yes.
But
Yes,
there you see, the context there was that, under the action of deforming forces,
Yes.
external deforming forces, the body does not get deformed.
Yes.
And such bodies we call it as rigid bodies. Right, that's
Yes.
it. But in this context,
Yes.
that is rigid body dynamics, something more we have to see.
Yes.
Okay, what is that more thing we have to see? What we have to see here is the body is consisting of particles,
Yes, sir.
and
Yes.
there is some distance between the particles.
Yes, sir.
Same matter.
So this distance between the particles
Yes.
will not change when the
Yes, sir.
body is under motion.
Motion. Yes, sir. Yes.
Understand? So that distance will not change. I suppose you got
Yes,
it,
sir.
right?
Yes, sir.
So in this context, this definition becomes very much more predominant.
Yes, sir.
So that is what I would like to put it across.
Yes. Sir.
Okay, fine. That is point number 1. So here you see, since I said the body consists of particles. Okay. Now we have studied particle dynamics.
Yes, sir. Yes, sir.
So we have seen a particle in motion, and we introduced this concept called particle. Please appreciate it. Concept called particle. There is nothing like a physical particle.
Yes, sir.
There is a concept called particle.
Yes. Sir.
So we introduced that concept called particle. Okay, and we said, well, this particle is so small in dimension that it has one property, that is inertial property, or the mass of that particle is m.
Yes.
Yes, sir. Yes, sir.
And since it is so small, it has no shape and no size.
Yes.
Yes, sir.
And what else did we say about this particle?
It can only have translated.
Yes, it can only have translatory motion. Only translatory motion. Correct. What else? It can have only translatory motion.
About like we.
Correct. It will have only translatory motion. Can you slightly emphasize that?
Cannot have.
Yes, louder.
It cannot have.
It cannot have rotational motion.
Yes.
So a particle can have only translatory motion. It cannot have rotational motion. On the other hand,
Yes. It can.
a body formed by the particles
Yes, sir.
can have both translation. So it does not have rotational motion.
Yes, sir.
Okay, this is. So I suppose you have got the picture of this. So, but a body formed by this can have both the motions, rotation, translation, and combined motion, and all this.
Yes.
Right. Now, our idea is whatever theory we developed to learn the dynamics of a particle, whatever theory we have developed regarding motion of particles, that is, all that equations of motion that we have developed, and even we considered the planetary motion. That is, Earth is revolving around Sun. Even Earth, we considered it as a particle, and we have
Yes, sir.
Yes,
Yes, sir.
Yes. Yeah.
right. So we have used the concept of particle wherever it could be used and to get the right abstractions out of it.
Yes.
Okay.
Yes, sir.
Now what we do is we will systematically develop a theory. Okay. From whatever theory we have developed for particles. Okay. What I mean to say is now if you take only one particle, then you know there is only one particle, and this particle is moving along this path.
Yes.
Okay, then we will discuss, you know, what are all the aspects involved here, and then what we do if you take a body, or before we take a body, we will take a rod, a thin rod.
Yes, sir.
We will take a thin
Yes.
rod, and it is easy for us. Now this thin rod has got what? The thin rod has got locus of particles. The thin rod has got locus of particles, and this locus of particles is along a straight line.
Yes.
Yes.
Is along a
Yes.
particular direction, so it becomes a thin rod.
Yes.
So we will develop the theory for this thin rod. So dynamics of thin rod.
Yes.
We will develop the dynamics of thin rod
Yes.
from
Yes.
the dynamics of particles.
Party.
We move on. Okay? All right. So therefore,
Sir, then why do we call the thin rod as a rigid body?
because the particles in that will not the distance between any two particles in that so-called rigid body, see, in that rigid body will not change under any circumstance.
So, sir, rigid body basically means it cannot be deformed in any possible.
Correct. It cannot be deformed in it will never be deformed theoretically, but practically yes, it will undergo very, very small deformation. And for all practical purpose, when we say it is rigid body, that deformation is negligible. Okay?
So, sir, okay, sir. So, practically, if the deformation is very, very small, we can call it a rigid body.
Excellent,
But
excellent.
ideal rigid body can't exist.
Yes, excellent, excellent abstraction. Correct? Understood? Okay. Now, I think this diagram is familiar to all of you. Hello, can you all see this diagram?
Yes, sir. Yes. Yes.
So, so what are the things that you see here?
So, the position vector of a particle is the angle it is making with the positive direction of the XI.
Okay, fine. Somebody else also.
Trajectory of
A directed line segment that you see there is the path of the particle,
yes.
right?
Yes.
Then what else do you observe here?
So like every point.
Its position vector at a point.
Excellent. See, I want these keywords. So the particle at point P, okay, with respect to a reference point. See,
Yes.
we are discussing the motion. Motion is always with respect to reference. So this
Yes.
diagram, in this diagram, you see a reference point O and a reference direction X.
Yes.
Yes.
You have to fix it. You have to fix it. Okay. Now you please appreciate and understand this very carefully. Reference point is extremely important. Reference direction is extremely important. Then we mark the position of the particle P by a position vector R bar. I am sorry, here only R is shown here. It should be R bar.
Yes, sir.
Okay.
Yes.
That's it.
Yeah.
Now all of us know that here. All of us know that any point in space, you can address that point by coordinate system.
Yes, sir.
Cartesian
Yes.
coordinates, cylindrical coordinates, spherical coordinate system, so many other coordinate systems you can address. So we are all familiar with the Cartesian coordinate system. So if it is three-dimensional space, we would have said that this P is X, Y, Z, and I suppose all of you know what is this X, Y, Z.
Yes.
Now,
Yes, sir.
in the study of rigid body dynamics, there is another way by which we can address it. So I think if you can recapitulate and tell me that there is a theta r that is given there.
R and theta.
Polar coordinate.
Yes.
coordinates.
Polar coordinates. Okay. So the position of the particle is marked with respect to the axis by what?
Polar.
By polar coordinates. That is, if I say the particle is at P1 and I will say P1, the coordinates of point, I will say P1 is x1, y1, z1, or the same P1, I will write it as r1, comma, theta.
Yes, sir.
What is this? This r1 happens to be this length and theta happens to be the angle made with respect to the x-axis.
Yes.
And if there is
So
another
we
point.
can use this only for two-dimensional.
Excellent. I was coming to that point. So this point, supposing P2, then it will be R2 theta. So on and so forth.
Yes, sir.
And as your friend has rightly pointed out, I wanted to ask you the question here. That is, here you see this polar coordinate system is for a plane too.
Yes, sir.
Only plane. It is not three-dimensional coordinate. This can be extended to three-dimensional coordinate.
Yes, sir.
No doubt about it. We have to add one more dimension to this.
Yes.
Okay, that is precisely what we call it as the cylindrical coordinate system or the spherical coordinate system. Okay, cylindrical coordinate system or the spherical coordinate system. There are different. I will be teaching you those things. Okay, I will be teaching you those things. So in the case of a spherical coordinate system, we will have r, theta, and phi.
Fine. Yes, sir.
I'll tell you what is this r, theta, phi. Okay,
Yes.
and in the case of cylindrical coordinate system, in the sake of cylindrical coordinate system, it will be r, phi, and z. I'll tell you all these things.
Yes.
These are the three-dimensional variables which I will teach you. But right now, we will only consider planar motion of the particle, and one of the ways of addressing the point is by mentioning its position vector r bar. Okay, and when we say position vector r bar, see, if I say this is position vector r bar, okay, because r bar, if I say, that means it is a vector. It's a vector. Okay, fine. So with respect to this point, this is a vector. Okay, you don't need, please appreciate and understand here. You have to understand that, you know, that this is the origin, and if I use position coordinate here, r1 bar, okay, I don't need any axis or anything for that.
Yes, sir.
Understand? See, now you see, there is a hill, okay, and there are houses here at the foothill. So if you take this as a reference point, so where is this house? R1 bar. Okay, where is this one? This house? R2 bar. That's it. Because R1 bar, R2 bar will tell you the it are the position vectors.
With respect to that.
So you are addressing that with respect to this point. Okay. But now you should know, like, you should have a definition for R1 cap. What is R1 cap? What is R2 cap? That you should have.
Yes.
So therefore here, so in this case, when this line is drawn like this, and this O is marked here, X is marked here, so this line is R. Okay, and this angle is theta. We are not using here R bar. If you want, you can use, but be careful when you use that. You know, you have to say R cap, etc., etc. And what is R? If it is R bar, R is only the magnitude of the position.
Yes.
Magnitude of the position. So you must be cautious, you know, when you use these two things. Clear?
Yes, sir.
Yes,
Hello?
sir.
Now, if I say this is x-axis and this is y-axis, sorry, this is y-axis, then this point, as I said, is generally r, comma, theta.
Yes.
And if I want to put it in the form of x and y, then what is x? If I give you r and theta, what is x? R cos theta. R cos theta is x. And what is y? R sin. Clear?
Yes, sir.
Okay.
Yes.
Now, supposing I don't give you theta, I give you phi. Then what is x?
R
R
sin phi.
So this
R
becomes
sin phi.
r sin phi.
Y is
Okay.
r cos phi.
Phi is R cos phi.
R
Yes.
cos phi.
Okay, done. So my job is done. Okay, fine. Good. Okay. Now, let the particle move from locations P1, P2, P3, etc. in the plane of paper. Let the positions be R1, theta 1, R2, theta 2, etc. So I think all of you, if the particle is moving, then you can see that the coordinates are also moving, changing.
Yes.
Now, what is most important is one point will have only one set of coordinates.
Yes, sir.
Yes.
Yes, sir.
So you can not use the same set of coordinates for
Yes, sir.
others. Okay.
Yes.
Here,
Aram se learn now, all of you. Now I'll give you some cases. You try to put it. I hope all of you can read this.
Yes, sir.
yes, sir.
Yes, sir.
Right. If case 1, see now with respect to this figure, so I will say now P1 is addressed by R1 bar, P2 is addressed by R2 bar, P3 is addressed by R3 bar.
Yes, sir.
Yes.
And so the angle made is theta 1, theta 2, theta 3.
Yes, sir.
Okay?
Yes.
So now, if the condition is R1 cap is equal to R2 cap is equal to R3 cap, the particle is in motion.
Yes, sir.
Yes, sir.
R1 cap is equal to R2 cap is equal to R3 cap. The particle is in pure translation with respect to the reference O, straight line.
Yes, sir.
Yes.
Now, can you, pardon?
So there can be another case, like if they have not mentioned that it is in motion, then it can also be a test. Where the magnitude of R1 bar.
See, gentlemen, I said the particle is in motion, the particle is in pure translation with respect to pure translation means it is in motion.
Yes, sir.
See,
Yes.
see, don't be hyper to ask questions. I am seeing you now. Today you have become very hyper. Don't. Be cool. Just be calm and cool. Okay, read aram se, and if you don't understand something only, you prompt. Okay. Now, can you in your notebook draw this condition? Lego. Please draw this condition. I am seeing here. I am seeing your couple of friends. Sure. Yes, correct. One friend has drawn it correct, other friend has not drawn it correctly. Yeah. So the fact here is R1 cap is equal to R2 cap is equal to R3 cap. Theta 1 is equal to theta 2 is equal to theta 3. But R1 bar is not equal to R2 bar is not equal to R3.
Yes, sir. Yes,
So if that mathematical condition is given, then physically you can see that with respect to this, so this one is the position of the particle R1 bar, and this is theta 1, and next when the particle is here,
Yes,
so
sir.
this becomes
Yes, sir.
R2 bar.
Same.
But this becomes, now with respect to that I am saying it's theta 2, and when the particle is here, it is going to be R3 bar, and this angle is going to be theta 3. But what we find here is that theta 1 is equal to theta 2 is equal to theta 3, and R1 cap is equal to R2 cap is equal to R3.
Yes, sir.
So what it means is,
Yes.
now as the particle is proceeding, as the particle is in motion, and at every point if you address it by its position vectors, okay, and it's also that at time t1 it is here, time t2 here, time t3 here, okay, and if these conditions are satisfied at every instant of time. What did I say?
At every instant of time.
See, that is important. At every instant of time. Okay, then the particle is performing pure translation with respect to O.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
That is should be interesting. So at every instant of time, okay, this condition is satisfied. Then with respect to it is performing translatory motion. Clear? Now you see, if you forget any one condition, that is at every instant of time. See, you may find that the particle is here at some instant of time, at some instant it is here, some instant it is here. So you are measuring the three instants. Which are the three instants? T1, T1, T2 and T3. Supposing you had also measured it at some instant in between T1 and T2. Supposing you had measured its position at some instant T1 and T2. At that instant, supposing the particle was here.
Yes.
Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Then it is not translative motion.
Yes, sir.
Yes, sir.
So, irrespective of whichever instance I choose, these conditions must be satisfied.
Yes, sir.
So,
Yes,
therefore, we say here for all T.
Yes, sir.
For all T,
Yes.
this should be satisfied.
Yes, sir.
Yes.
Sir, one doubt.
Huh.
Now, sir, we are taking a particle, sir, and we know that particle will always travel in translational motion. So, sir, why these conditions have to be satisfied for translation?
Excellent, excellent.
For a straight.
So, you
Yes.
please read, you please see here. See, I have now started using these words. A particle is in pure translation with respect to a point O. So, that word pure translation here, see that word pure translation is I have added one word pure to simply the translatory motion.
Yes.
Understand? So it means now pure translation you should infer it as what? It's a straight line motion.
Okay, sir.
You should infer it like that. There is nothing like impure translation motion. Okay? There is another word that will come here. So we will use this. So it is pure translation means it is moving in a straight line. Okay. Now here you see. Now this is with respect to point O. Okay. Now you see the same motion of the particle. If instead of O, if I have chosen another reference O dash. If I have chosen another reference O dash. Okay. So I will choose another reference O dash. Okay. And I will say yes. The particle is here, here, here. Okay. This is another reference O dash. Now with respect to again this is x-axis. Now this becomes R1 bar. This becomes R2 bar. And this becomes R3 bar. Okay, now do you say the particle is in pure translatory motion?
No, sir.
Not with reference to the given fixed point, sir.
Okay,